I of y of x is equal to integral from 0 to 1 by 2 y dash square plus y dash plus y dash plus y dx if the values at the end points are not given, subject to the condition not given. For the minimum of the functional I of y of x 0 to 1 is equal to 0 to 1 integral 1 by 2 y dash square plus y dash plus y dash plus y dx. The integrand f is equal to 1 by 2 y dash square plus y dash plus y dash plus y must satisfy Euler's Lagrange differential equation. Therefore, del by f by del by y minus d by dx of del by f by del by y dash is equal to 0. Here del by f by del by y dash, what is y dash plus 1, and del by f by del by y dash what is y dash plus y plus 1. Therefore, y dash minus plus 1 minus d by dx of y dash plus y plus 1 and differentiating y double dash plus 1 and y dash y double dash plus y dash plus 0. Therefore, y dash plus 1 minus y double dash minus y dash is equal to 0. Y dash cancel. Therefore, y double dash is equal to 1. Integrate. Y dash is equal to x plus c1. Into again integrate. Y is equal to x square by 2 plus c1x plus c2. Where c1 c2 are constant of integration are to be determined. However, note that the value of y at the end points are not prescribed. The constants are determined from the condition del by f by del by y dash at x is equal to 0 is equal to 0 and del by f by del by y dash at x is equal to 1 is equal to 0. This implies that y dash plus y plus 1 at y is x equal to 0 is equal to 0. Y dash plus y plus 1 at x is equal to 1 is equal to 0. Therefore, combining this, y dash of 0 is equal to c1, y of 0 is equal to c2. Therefore, y dash of 1 is equal to 1 plus c1 and y of 1 is equal to 1 by 2 plus c1 plus c2. Therefore, this equation becomes c1 plus c2 plus 1 is equal to 0 and 2c1 plus c2 plus 5 by 2 is equal to 0. Solving this equation for c1 and c2 and we get c1 is equal to minus 3 by 2 and c2 is equal to 1 by 2. This equation hence the required curve for which the functional given in 1 becomes minimum if is y is equal to 1 by 2 x square minus 3x plus 1. There is one more theorem for Euler's Lagrange differential equation of motion. Find the Euler's Lagrange differential equation satisfied by 4 times differentiable function y of x which extremizes the functional I of y of x is equal to integral from x1 to x2 f of x y dash y double dash dx under the condition that both y and y dash are prescribed at the endpoints. Let p of x1 y1 and q of x2 y2 be two fixed points in xy plane. The points P and Q can be joined by infinite mini curves. According to the value of the integral, I will be different for all different paths. We look for a curve along which the functional I has an extremum value. Let's see be a curve. Let's see be a curve between P and Q whose equation is given by y is equal to y of x0. Let also the value of the functional along the curve C be extremum and is given by I of y of x is equal to integral from x1 to x2 f of x y dash y double dash dx. We can label all possible paths starting from P and ending at Q by the family of equation y of x alpha is equal to y of x0 plus alpha eta of x, where alpha is a parameter and eta of x is any differentiable functions of x. For different values of alpha, we get different curves. Accordingly, the value of the integral I will be different for different paths. Since y and y dash are prescribed at the endpoints, this implies that there is no variation in y and y dash at the endpoint, or that is all the curves of the family and their derivatives must be identical at fixed point P and Q. This implies that y of x1 alpha is equal to y of x1 0 is equal to y1, y of x2 alpha is equal to y of x2 0 is equal to y2, and also y dash of x1 alpha is equal to y dash of x1 0 is equal to y1 dash, and y dash of x2 alpha is equal to y dash of x2 0 is equal to y2 dash. This implies that eta of x1 is equal to eta of x2 is equal to 0, and eta dash of x1 is equal to eta dash of x2 is equal to 0. Conversely, the condition 3 ensures that the curves of the family of the that all pass through the point P and Q. Let the value of the functional along the neighboring curve be given by I of y of x alpha is equal to integral from x1 to x2 f of x y of x alpha y dash of x alpha y double dash of x alpha dx. From the differential calculus, we know that the integral I is extremum if da by f by da by alpha at x is equal to alpha is equal to at alpha is equal to 0 is equal to 0, because for alpha is equal to 0 the neighboring curve coincide with the curve which the extremum value of I. Thus da by I by da by alpha at alpha is equal to 0 is equal to 0. Therefore integral from x1 to x2 da by f by da by y eta of x plus da by f by da by y dash eta dash of x plus da by f by da by y double dash eta dash of eta double dash of x dx is equal to 0. Integrating, therefore da by f by da by parts, therefore this is on, and eta of x1 is equal to eta of x2 is equal to 0, there is no prescription, and eta of x eta dash of x1 is equal to eta dash of x2 is equal to 0, and so on. Therefore da by f by da by y minus d by dx of da by f by da by y dash plus d2 by dx square da by f by da by y double dash eta of x dx is equal to 0, and by basic lemma of calculus of variation da by f by da by y minus d by dx of del by f by del by y dash plus d2 by dx square del by f by del by y double dash is equal to 0. This is required Euler Lagrange differential equation. So to be satisfied by y of x, for which the functional I has extremum value. I has extremum value. काय कर